Hello everyone, my name is Ali Mohammed. Today I'll be presenting our paper Enhancing Condition Monitoring with Virtual Reality Visualization for Industrial Applications. So I'll first start with an introduction, then I'll move on to the design and implementation, which will include the hardware setup and software design. Then I'll discuss the results of the hardware implementation, PLC software, and VR application, and finally the conclusion. So in any industrial setting, the critical importance of continuous production is very important. And in these environments, any equipment failure can result in significant losses. That's why monitoring machine operation parameters, it's not just like a good practice, it's a necessity. And by assessing maintenance requirements preemptively, we can optimize the equipment performance. This optimization, it will not only just reduce the cost, but also guarantees the continuous operation of a machine. And it will also safeguard against any potential disruptions in the industrial process. So unlike traditional time-based maintenance, condition monitoring can not only estimate the health of a machine, but provide information on the performance and maintenance required based on real-time data. And there are many condition monitoring methods, such as thermal monitoring, current analysis, or signal processing, the vibration analysis. These techniques are used to acquire data and then process it to obtain results, which are typically presented in graphical interfaces. In recent years, there have been a growing interest in the use of virtual reality and augmented reality for condition monitoring. Now, both of these technologies allow for immersive real-time monitoring of equipment, and it enables maintenance personnel to quickly identify and diagnose problems. They also allow remote monitoring, which can be particularly useful in situations where it's not practical or it's not safe for maintenance personnel to be physically present at. One of the key advantages of VR for condition monitoring is the integration of haptic technologies, which create the experience of 3D touch for the user by, by applying vibrations or motions. And this can be particularly useful in training maintenance personnel and familiarizing them with the equipment, which will reduce the risk of errors, basically. Now, VR has already been used in a variety of fields, including like education, landscape design, but the application in industrial settings is still relatively limited. So the proposed system aims to present a novel visualization of monitoring equipment in virtual reality. The conceptual diagram of the proposed system is shown here. So the system consists of three parts: the data acquisition, visualization, and an MQTT broker. Both the data acquisition PLC and the VR headset are connected to the MQTT broker for the internet. The first part of the system is the data acquisition. So a Beckhoff programmable logic controller, or a PLC, will be used to acquire data from one vibration sensor. The PLC is basically a widely used industrial control system that can be programmed to perform a variety of tasks. And in this case, it will be used to acquire data from the vibration sensor and then analyze it and then publish it to the MQTT broker. Now, the VR headset will be subscribed to the MQTT broker and receive the analyzed data for visualization, which is the second part. So the second part of the system is the visualization. The VR headset will have a Unity developed application with a 3D model representation of a motor or a machine that will visualize the health of that machine or motor with data from the MQTT broker. The VR headset will allow the user to configure the MQTT broker settings, set up the sensor locations, and view interact with the motor in real time through the VR application. And this can be particularly useful for maintenance personnel as it allows them to quickly identify or diagnose problems with the equipment. Now the third part, or it will be the MQTT broker. So the broker, it will just serve as a central hub for communication between the data acquisition setup and visualization. It will receive the published data from the PLC, and the VR headset will be subscribed to retrieve this data. which will allow for the real-time visualization of the health of the machine. So the system consists of two main components, the controller and the sensor, as seen in the figure. The PSC utilized is a Specov CX5130 embedded PC, which has an Intel Atom processor and 4GB DDR3 RAM, and it's running Windows 10. The PSC is of course powered by a 24 volt power supply, and it also has an ELM3602 IEPE measurement terminal, which has a max sampling rate of 50,000 samples per second. The system also will have an SPM IEPE SLD144TB vibration transducer, which is mounted on a single phase motor to test the concept of the proposed system. And an eccentric load was mounted on the shaft of this motor to basically simulate the vibrations that can be picked up by the vibration sensor. And the software design is divided into two parts. So the PLC is employed for acquiring data from the vibration sensor, and it utilizes TwinCat3, which will also analyze the data and then publish the results to an MQTT broker. So the program was developed with structured text programming language and is then deployed on the PLC. TwinCat3 Analytics Workbench, which is a graphical user interface, is used to create and deploy data analysis programs. The condition monitoring library in TwinCat3 is also utilized for the vibration assessment. The PLC program is then triggered by the MQTT parameters and the start signal which it will get from the VR application. After it will start doing the real-time analysis and publish the results back to the VR application. The second part is the VR visualization. So Unity, which is a 3D game engine, is employed for creating interactive applications. And in this case, it was used for visualizing the health of a motor. The M2 MQTT library in Unity is used for data exchange between the VR application and MQTT broker. The VR application will also allow for configuring the MQTT settings, the motor settings according to the ISO 10826-3 standard, and will also allow you to import a model for visualization and the sensor location setup. Also, we have a Unity shader, which is used on the 3D motor model to generate like a heat map based on the sensor locations and the vibration analysis values. And this will provide like a dynamic visual representation of the motor's condition or machine's condition, which would ultimately enhance the accessibility and enable real-time assessment for effective condition monitoring. The data acquisition setup is shown here. So the single phase motor with the vibration sensor can be seen on the right. The PLC will be acquiring the data from the sensor using the measurement terminal, and then it will perform analysis on the acquired accelerometer data according to the ISO 10816-3 standard and classification configuration, which is taken from the VR application. Finally, it will publish the results of the vibration assessment to the VR application using the MQTT broker. To perform the vibration assessment according to the ISO 10816-3 standard, which involves measuring and evaluating vibrations in machinery, the assessment criteria is based on the root mean squared RMS value of the vibration velocity or displacement. So according to the ISO standard, the motor used in this experiment cannot be categorized since the motor power output is rated less than 15 kilowatt, and the minimum for the standard is to be within the output power range of 15 kilowatt to 300 kilowatt. Therefore, it will be considered that it's in group 2 for just simulation purposes. The PLC will first buffer the input data from the sensor since the test motor has a speed above 600 RPM, which complying with the ISO standard, the frequencies in the range of 10 Hz to 1000 Hz will be evaluated. So fast Fourier transform, or FFT, is used to analyze only the specified frequency range. Then the RMS values for the acceleration data is calculated. Additionally, the RMS value of the vibration velocity and displacement are basically calculated from that acceleration data that was acquired. So the RMS value of the vibration velocity and displacement are basically calculated from the acceleration data, and the RMS value of both of them are then checked against the ISO standard limits for machine 2 or machine group 2 to determine the classification. So the ISO standard defines 4 zones: A for like recently commissioned machines, B for machines suitable for continuous operation, C and D are basically for unsuitable machine and those which are considered dangerous. So these zones, as you see in the table, they just serve as a guideline based on the machine condition. And the limits described by the standard are more or less only intended as a general guideline, and in some cases it cannot be applicable to certain machinery, just like in our case. So the worst case classification is usually determined by comparing the two possible outcomes that you have from velocity and displacement. So after that, the classification results which you are getting are published to the MQTT broker for the VR application. The graphs here showcase a sample of the acceleration data which is acquired from the PLC. The part in red shows the normal operations of our motor that we have, while the green was produced by simulating some vibrations on the motor so that we can visualize it later on in the VR application. So the Unity application was developed and installed on the Quest 2 headset, which would enable the user to move around in the virtual world and interact with a 3D presentation of the motor. So after starting the VR application, the user will be presented with the main menu as shown in the figure. The first step is to set up the MQTT broker configuration, so the broker address, the port, subscription topic, username and password if applicable. After that, the user can test the communication connection to check if the VR application is able to communicate with the MQTT broker. The user then must set the number of sensors and the MQTT topic of each sensor. They are also able to test the MQTT communication for sensors to see if the data is being received. The user will also be able to set the motor configuration as per the ISO standard, which is the ISO 10826-3 standard, and publish it to the broker, where the PLC will be subscribed to read and set the values for analytics. Optionally, the user can also import their own motor or machine model if they would like to, instead of the default 3D motor model, and then set the sensor points as shown in the figure on the right. Finally, after starting the measurements, the user will be able to see the motor overview or machine overview with the details of the sensors and evaluation zones. And as per the vibration velocity and evaluation zones received from the PLC, the shaders of the 3D motor or machine will start to display a heat map based on the previously placed sensor points. Alternatively, if there is more than one sensor, touching the sensor placeholder or selecting it will show an overview of the sensor with its values. So in conclusion, the proposed system integrated a backup PLC for data acquisition and a MetaQuest 2 VR headset for visualization. So the system allowed the user to view and interact with the device or machine in real time for the purpose of evaluating the health of the machine. The use of virtual reality for condition monitoring has the potential to significantly improve the efficiency and effectiveness of maintenance operations in industrial settings. It can also help to reduce cost, improve productivity, and ensure the continuous operation of the equipment. As virtual reality technologies continue to advance and become more widely adopted, it is likely that we will also see an increasing number of applications in the industrial sector. So further work can be achieved to enhance the system. This could include mapping the results of multiple sensors and perhaps applying artificial intelligence predictions on the motor status to assess the operators and engineers in the field.
And if you have any questions, please feel free to contact us.